So we're going to switch gears now and talk about another success of the old quantum mechanics. And this time we will talk about the Bohr atom. As you know, Rutherford discovered some important facts about the atom. He discovered that the atom mostly consisted of a nucleus at the central core and surrounded by empty space. But in this empty space, the electron orbited the positively charged nucleus. So it looked something like this. So we have a heavy positively charged nucleus, say, whose atomic number is Z, and so it has some charge. And then around that nucleus, the electrons went around, something like this. Now there is something wrong with this picture because, well, first of all, this is a very planetary model, if you like. But instead of the centripetal force on the electron being provided by the gravitational force, it's provided by the Coulombic interaction. So this is the force direction. But we know that when a charge accelerates, it radiates. That's something we know from classical electromagnetism. So if the electron is going around in a circle, of course it has to accelerate because otherwise it would go straight. So, and if it does accelerate, it should radiate, and therefore it should lose energy quite rapidly and fall into the nucleus. So according to classical physics, the Rutherford model of the atom should not be stable. So something was wrong there. To solve this problem, Bohr proposed almost ad hoc two assumptions. He proposed that the atoms at the quantum level, they have what he called non-radiating stationary states. So these are states in which you calculate the orbits of the electron using classical physics, but by fiat, he announced that they are non-radiating. And because they're non-radiating, the total energy of that state doesn't change. And that's why they are stationary states. The other thing that he assumed was that suppose that we have two energy states of this atom, and one is, say, EM, and another one is En, and the transition between them cannot be predicted from classical physics. Instead, it will happen in the following way. Suppose the energy state Em of the atom is higher than the energy state of the atom at En. Then if the atom is in the higher energy state, then it can jump through a non-classical mechanism, which is now called the quantum jump, but it radiates away the energy difference as a photon, and the energy of the photon is given by the h times nu. So, or in other words, the energy of the photon that is emitted is given by Em minus En, and its frequency is given by this difference divided by Planck's constant h. And conversely, if the atom was in the lower energy state, then it could absorb an incoming photon, whose energy was exactly equal to the difference between these two states, and then it could jump up to the higher energy state. So these are the assumptions that Bohr made